Our next panel, AI for Energy Innovation, will now begin. Moderating the discussion will be Dr. Olga Spahn, Program Director at the Advanced Research Projects Agency for Energy. Please welcome our speakers. Dr. Peter Battaglia, Research Scientist at Google DeepMind. Dr. Stephen Cowley, Director of the Princeton Plasma Physics Laboratory. Dr. Phil Larochelle, Partner at Breakthrough Energy Ventures. And Dr. Brian Spears, Director of the AI Innovation Incubator at Lawrence Livermore National Laboratory.
Okay, are we ready to start?
No, you didn't. But
Okay, so just one more time, a very brief introduction again. We have Peter from Google. We have Steve from Princeton Plasma Physics Laboratory. We have Phil from Breakthrough Energy Ventures. And we have Brian from Lawrence Livermore National Laboratory. I'd like to start with a general question to the panel. What are the expectations for application of AI to the problem of energy advancements before us? And what kind of revolutionary changes can we expect given the cost of AI, is, as we heard, is going to be considerable in terms of energy needs. So let's start with you, Peter.
thanks. So I see potential for AI to address energy sort of across the board in energy. Similar to what Eric said, AI is a sort of accelerator of science generally. So I think we can think about the different parts of energy, right? So advancing supply, I think with AI-driven forecasting, renewables forecasting, also introducing new supply, new technologies for supply, batteries, new materials, things like this, reducing demand or managing demand. So things like data center, optimizing the loads at data centers, and also better demand response, things like that. And also, I think advances in transporting the supply to the demand. Grids are obviously a huge problem. We need to manage the existing grids better, but also accelerate how we plan new grid and new interconnect. As far as this sort of potential for revolutionary change and how to kind of just confront the reality that AI will also increase our energy load. I'm very optimistic. I think that AI is a very powerful tool. I, as a sort of director of the sustainability program at Google DeepMind, our mission is literally to revolutionize environmental sustainability with AI. So you better believe that we're aiming for revolutionary changes and we're sort of going all in on AI. And what we're seeing in the field is, the reality is we're seeing that the advances in weather forecasting, some early signals from energy modeling are suggesting that revolutionary change is on the horizon. And so we expect these types of things will continue and show tremendous payoffs for us.
Thank you. Steve, what are your thoughts on that?
AI is already doing. AI has solved science problems that we thought were going to take decades to solve. The AlphaFold problem, DeepMind worked on. And in energy, it is making inroads. But that kind of revolutionary change, I work in fusion, and I think it can make that huge difference to the timescale to get to fusion. Because at this point, we don't quite know how to do that. It may be the first technology that's actually enabled by AI. And by enabling fusion, you might enable AI because you will then power your data centers with fusion. It's just amazing in the last 3 years how many things have changed because we have AI attacking problems and solving problems in science in a way that I didn't think was possible. It's a bit dizzying.
Great. Now, for investment perspective, from Phil, what do you think?
Yeah, so I'm a partner at Breakthrough Energy Ventures. This is an organization started by Bill Gates and a few dozen other like-minded individuals from around the world, which is how do you help tackle climate change with innovation? So when it comes to AI, and you heard it from him before, it can really have a profound effect kind of in 3 domains. So the first I would say is on the demand side. And I think you're going to hear a lot more about that today. You've already heard about it. A couple of our companies are going to be on the panel later. So now having a group of people who are very interested in a social license for infinite energy consumption, something which is sustainable, that can have a huge impact. But in terms of the AI for energy, in terms of the supply side, how can AI make the supply of energy better? I think there's both evolutionary changes and then there's revolutionary changes. And so the evolutionary stuff, it's kind of like the first computer revolution, which is like anyone who doesn't use like a personal computer or a spreadsheet or computer-assisted design is just going to fall behind. And so the evolutionary changes are, if you don't adapt these things into your day-to-day business, you're just going to fall behind the competition because they're going to be able to do things a lot better. So we have over 100 companies. At this point, I think if you ask them, they will all say that they have an AI strategy. But in particular, I would point to a couple of our mining companies like Cobalt and Geologic AI that are really using AI, big data to really kind of move ahead of the competition in terms of prospecting and finding new critical materials. And then even things like deploying solar plants. So we've got a couple companies, Planted and Terra-based, that are using AI tools to both design very large scale, gigawatt scale solar plants, but then also starting to incorporate that in the automation of the deployment. So that's all evolutionary, and that's going to keep going, just like computers have become more ubiquitous in every aspect of business. But the really revolutionary changes, those are hard to predict. So Stephen kind of mentioned some of the stuff that's happening in fusion, a lot of the great stuff coming out of PPPL. That could be a big change in terms of bringing it to the grid. But then I think what was mentioned by Eric, which is also just the advancement of science that could happen by incorporating AI tools. We saw what happened on AlphaFold. But in terms of new materials discovery, I think what we're really excited about is coupling AI with other things that we know that can help. So for example, quantum computation, if you can simulate physical systems quantum mechanically rather than with a classical computer, you can now get much more fidelity. And so it's very interesting to think about a loop where you have AI-informed experiments that are doing some experiments normally, some experiments in the physical world, some very high-cost quantum simulations. How fast can that loop keep going? And then we think that there's all kinds of applications like that. But, the evolutionary changes are definitely happening. The revolutionary changes, we'll see how impactful those are.
Okay, and then finally, Steve, what's your thought on this?
Brian.
I'm sorry.
But that's okay. I'm going to riff, though, on what Steve and what Phil said. So what can our expectations be? Definitely that AI can transform energy production. So I've also worked on fusion at Lawrence Livermore. We've used AI to help us understand that mission space. I think we should have an expectation that energy is actually going to drive and benefit AI. So for some of the things that you mentioned, Phil, these loops where AI systems can control and drive our science forward are fantastic for the science. They're also in critical need for the AI. So we heard some questions about enhanced reasoning or general reasoning. To do that, you need better tasks, harder problems to go solve. You need more data to go get. And the energy approaches that we take are going to demand that. High-speed control of magnetic reactors, inertial fusion reactors with high repetition rates. These are sources and fountains of data and reasoning problems about what happens when you get stuff really hot, when you make it go fast, when it's very dense. Our AI capabilities have not seen this in the commercial tools that are evolving, and so there's going to be a positive pressure back on those systems as well, and then it's a virtuous cycle. We can bring those better reasoning systems for science together to do fusion research, fusion energy, and drive the entire ecosystem forward. There's an entire undercurrent there of what the public sector can do through national labs and the Department of Energy, since we were fortunate to hear about the FAST program from the Secretary earlier, but we have to do it with private partnership as well. So will it be evolutionary or revolutionary? I think it's definitely going to be revolutionary, but it will come through something that looks like it was an evolution. Being able to do those reasoning loops and execute that science at such pace that it feels like magic, and that in and of itself is going to be a revolution.
So speaking of revolutionary potential of AI and things it can do not just for energy, but for science in general, what would you say are the biggest obstacles facing AI in science?
Well, we need a more pronounceable acronym, apparently. So FAST is a thing that we can think about. But the biggest obstacle, I think, is coherence and will across this community and across government. So we do have a vision for what transformational AI for science can look like in that FAST program, which I will say again for you is Frontiers in AI for Science, Security, and Technology. That's a vision for the way that we can discover new materials that are critical for energy, for storage, for batteries, for fusion reactors and energy production. It's something that we can use for the design of those systems, that we can use in something that's often overlooked, which is manufacturing, the capability to drive high-speed and new advanced manufacturing systems, and then to deploy those systems. We have this really clear view for what we can do in the science world. It goes through public-private partnership where new reasoning systems will drive that. The only piece that is missing is our US will to go do that, and that will take funding. We've got a roadmap in terms of FAST. We just have to go execute this with our national labs and the rest of our US partners.
So oftentimes will is expressed as investment. And with that,
That's what I meant.
Speaking of investment, Phil, how do you evaluate potential of companies that are working on energy ideas that are so far out there that it's hard to tell whether that's even possible? Have you ever been tempted to fund something that goes contrary to current conventional wisdom?
Well, we only have so much appetite for risk within the ventures side. We have another more philanthropic earlier stage part of Breakthrough, which is called Breakthrough Energy Fellows. And so we've got a whole pipeline of how to get these new technologies to commercialization that we call, discovery, develop, deploy. But within the ventures side, we do screen out a fair number of things just because they, violate the laws of thermodynamics, but actually very few things actually do that. And then you really have to get into the realm of the story of commercialization, which is what's the market you're trying to address? What's the cost and performance you need to get traction in that market? And then very importantly, we always say, what would we have to believe for it to actually be a viable commercial product? And so, we try to think of not like, all the reasons why it won't work, but rather we say, what would we have to believe for it to work? And then I'll just say, we often say like, are you only going to fund things where there's a very good science basis? Well, it depends what you mean. I mean, there's a few things out there like high temperature superconductivity, which by the way is lower temperature than room temperature superconductivity, if you're confused. But there's not really a good theoretical basis for why that happens, but we know it does. And that's what's kind of interesting about the new world of AI, because I don't think people realize how much of the science that we understand is empirical. And so what we may have with AI is this whole new time period of where it kind of figures out nature faster than we do, and it has this looking in areas where we wouldn't have looked. And then I can see a time period and kind of a golden age of investment where there's all these things that nature can do that we didn't realize, that we start to, invest in more and more based on empirical evidence and the place where AI tells us to look.
Great answer. So, Steve, I have a question for you. Regarding the role of AI and optimization of the design of future fusion reactors, because that's one of the very promising areas people see applications of AI in.
We've had a good couple of years in fusion these last 2 years. The spectacular success at National Ignition Facility in actually producing an ignited fusion system that's never been done before, and it's the only place in the planet that's done. Simultaneously, last December, in the joint European tours in the UK, there was 10 megawatts of fusion power for 5 seconds, confirming a lot of the things that we thought we knew. But behind all that is actually what we really did in the last 20 years in fusion research, which was to understand what was really happening in the system in a scientific sense. All fusion systems have this one problem, that they're turbulent, and the heat gets out faster than you can supply it with fusion if you're not careful, right? And that turbulence was really not understood until about the last 5 years. But by now having a predictive understanding of that, we can kind of extrapolate into the future. But we looked at this at Princeton and we said, okay, could we actually make a virtual fusion reactor designed on the principles of this science that we now understand, which we didn't understand 10 years ago, and make a virtual fusion reactor? Well, it takes us about 3 months to calculate one fusion configuration. And that's just the physics configuration, right? And if we would search all parameter space, and we estimate there are about 100 billion essentially distinct configurations, this would be a quick route to choose. It'd take an awful long time. So what we can now do is we can use AI to learn from those predictions to emulate the high-performance computing. We don't have any data because we don't have any computers, right? But we do have numerical predictions of what might happen, and we can use that to train AI, which will shorten the calculation and allow us to search the optimal space for a fusion reactor. The difficult questions then become, what's actually commercial? What's cheap? Right? What's engineerable? What's maintainable? All those questions that physicists like me, we just want to make it work, right? But in the end, of course, we want to make electricity at a price the consumer wants to consume. But I think that fusion might be the first major technology that is essentially enabled by AI.
That's a great point. So another question for Peter this time. Another application of AI that's meeting success is your recent work on AI-based weather models that has significantly advanced forecasting accuracy. Can you tell us how the models that you're employing are different from large language models that you encounter in, say, ChatGPT, for example? And how mature are they, and what can we expect from them?
Yeah, thanks. So most people are familiar with large language models, at least in their everyday experience. The way they work under the hood is pretty simple. They take the text that you query it with, or the text that it sort of was conditioned on, and then they predict the next word. So our weather models work in a slightly similar way. They also take as input the current state of the weather, or like what we sort of, they condition on what we already know is in the past. But then they predict the next state of the weather all over the Earth, at many, many locations on the surface and in the atmosphere, all at once. So that's a huge, huge description of the next state. So they're outputting a much, much more complex description of what's expected to happen next. Another technology that you can compare these AI-based weather models to is traditional weather forecasts. So traditional weather forecasts work in a sort of similar way. They take the current estimate of the state of the weather and they predict the next state. But the way they're built is that engineers with expertise in the equations of physics that govern the atmospheric dynamics and numerical methods, they craft this simulator to simulate the next state of the weather. With our methods, we learn that from actual data, a catalog of data about the history of weather on Earth. So it's exploiting the statistical regularities in observed weather to make predictions about future weather. And one other difference between LLMs, large language models, and our weather models, large language models are sort of generalists, right? You can kind of ask them any question. The quality might sort of vary. Maybe it's a good answer, maybe it's a little off. By contrast, our weather models are specialists. They are very, very good at predicting weather very accurately and very efficiently. So now we can predict a 10-day forecast over the Earth that's the best forecast in the world in 1 minute on one device, where the top existing operational system takes about an hour on a supercomputer. And so I think in terms of maturity, where are we and where are we going? It's very hard to say. So I think it could be that we're going to see a lot of advances in AI weather forecasting. It might also be that we've sort of reached the limit of what we can predict based on the input data that we're providing. But I think most people agree that we really need to explore providing richer data about weather. And that can be coming from weather agencies, or it can be coming from weather-adjacent industries like the energy companies, and grid operators, and things like this, that talk about sort of the wind, the solar, the precipitation, hydro, things like this. And making that available to the AI community would be very helpful in allowing us to unlock more accurate weather and other sort of weather-adjacent problems.
So given what you said about the specialist nature of your models, right, but also very successful predicting a notoriously chaotic system like weather, is there an opportunity to apply similar techniques or models to other complex systems?
Yeah.
And what other big challenges can you address with similar approaches?
So I love this question because it's sort of, it just speaks to the sort of the central sort of thesis of what we've built our research program around, which is that a wide variety of complex systems, different complex systems, can all be sort of modeled by a similar set of deep learning methods. And so the weather models we developed are basically just like the next sort of evolutionary step in a lineage of models that we've been building for quite a while, where we've modeled things like automobile traffic on roads and molecules and catalysts and particle physical systems, astrophysical systems. What we're seeing is that these types of methods for learning simulation, to learning to simulate complex systems, are very effective at generalizing to many different types of systems. As far as what's next, a great example is actually work that we sort of have published preliminary work on recently, applying these same types of methods to power grids. So earlier this year, we released a paper on modeling grid, sort of making decisions about how to optimize power flow, in particular like sort of power dispatch on simulated grids. And we've released a data set alongside this. And this is a sort of preliminary work. We're kind of viewing this as kind of an early stage, but it's showing thousands of times speed ups over traditional solvers with almost no loss in accuracy. So I think we love the idea of getting into grids and energy because it's a tremendously complex system. It has all the sort of features of the systems we've attacked in the past and been successful on. So I think it's a kind of great fit.
That's really interesting. So given that AI is so incredibly powerful, it can be so incredibly powerful, I wanted to ask Steve you a question. Is it just AI that's going to get us there as far as fusion is concerned, or is there other parts like experimental work? You know, you need data, you need validation. So how much of the progress in fusion research do you attribute to the experimental breakthroughs versus improved simulation and modeling capabilities?
It's both. We spent since 1950 trying to make a fusion. And a lot of that has been the sort of Edisonian approach. Thomas Edison made 50 copies of it and chose the best version and then moved from that. The last 20 years has been that the science has actually caught up with experiments. And that's been the big change. And that allows you to go beyond where we have experiments. I mean, fusion experiments cost a lot of money, right? And we can't be Thomas Edison at $1 billion a pop. Right? It's just, nobody's going to give us that kind of money. So we have to be able to confidently extrapolate to fusion conditions so that we can actually, ask ourselves the question, what makes a good fusion reactor? What I was saying before, I think, is that the computation tools we have, they're very complex, they're very intensive on the use of computers. And the great thing that AI can do for us is to basically short all those predictions, make it possible for us to search the parameter space rapidly and converge on something that might actually deliver electricity at a cost the consumer wants to pay. It's a very exciting time. All of our graduate students are learning AI. They learned it as undergraduates. They're studying it as graduate students. They're applying it to every single problem. Some of those are kind of trivial problems, and some of them are like this one, which might really change the world.
Great. So another question for Phil. What would be the contrarian energy technology bet that you would make? And I assume you're bullish on the AI since you're here. But in the AI space, what goes counter to maybe prevailing wisdom today?
Well, I mean, look, obviously this is one of these mega trends that you have to pay attention to, and it exists on a spectrum. And so if you really think the singularity is near, maybe you go out and you invest in a company that's going to make Dyson spheres or something, but clearly that might be going a bit too far. But I think that, AI is one of those things where, sure, you get specific opportunities where you're like, here's a very specific AI application for something, and so let's bet on that. So you could, for example, have a materials discovery platform that is just trying to take some of the approaches that did before, which was high throughput experiments, and then couple that with AI and just see how far you could go with that. But I think that other than very specific technology bets, which we've done, and I mentioned that we did stuff in mining, we've done stuff in the automation of deployment of power plants, very interested in what's happening with weather. There was actually just another paper that came out in Nature yesterday about how much better these weather models are getting. What could you do with that? But I think, and I referred to it before, we very rarely dismiss a technology out of hand, although there's many we do. But what we always say is, what would you have to believe for this to actually make sense? And there, some of you may have come up across this. Elon Musk has this term which is called the idiot index, which is the ratio of the cost of the product to the cost of the raw materials. And, the question is, as you get new technologies, not just AI, but also additive manufacturing, all kinds of other stuff, do we now believe that these learning curves are accelerating? And do we now believe that you can reduce that idiot index so that you can get much closer to the cost of raw materials? And then if you do that, then you start to reconsider a whole bunch of technologies that you might have dismissed out of hand. So we might still be kind of far from the Dyson sphere, but, launch costs are coming down. Maybe robots can assemble stuff in space. Maybe you start to look at space solar again. So the point is I think AI has very specific applications, but a lot like computers in general, it is just this massive accelerant that then makes you look again at everything else that you used to dismiss.
Very good point. I do want to revisit a question I asked before with Brian. The models that are being developed for AI infusion, how are they different from the large language models that we use, in ChatGPT, for example? But also, how are they different from traditional machine learning approaches? Because these days seems like everything is AI. It's a buzzword, right? So is there really a fundamental difference?
Yes. I think that's a partial answer. I think Peter did a good job of explaining what scientific models look like compared to traditional models. I'll add another direction. We're going to use them for fusion. At our laboratory, we use them to think about the way that we will modernize and maintain our strategic nuclear deterrent, the way that we will build therapeutics for warfighters and for the general public. These are high consequence applications of these models. So a way that our models are different is that we have to understand what is our confidence. Can we quantify our uncertainty in the ways that we're going to use these? It's okay to serve an ad incorrectly 15% of the time. You can't be wrong about the things that we do at our laboratory. So we're embracing these tools because we can see routes forward to add more capacity to systems, to make us better able to reason. But how are they actually different? They're different because traditional ML systems allow you to recognize patterns, make decisions, go forward and do things that maybe it would have taken a human to do. These new systems have more capacity, and what is emerging is the ability to do things that are close to human capability. And the key word that is a centerpiece that I hope everyone takes away is the capability to reason. So increasingly, the direction that these tools are able to go is to have an answer, to verify that answer, to think about that answer in detail and make sure it makes sense and that it's useful. So it's aligned with that mission that we have where it's high consequence, and it's also a clear and distinguishing capability from things that have come in the past, that capability to reason. It also does something that makes them sort of our scientific tools similar with what's going on in the large language model world, which is that there's a clear sense of urgency. So another thing I hope everyone feels is that we have seen a global race sparked, a competition for superiority in the harnessing of these kinds of tools for high consequence missions, for energy production. We've got to go forward and understand exactly what that does. To seize that moment and actually do it, we can depend on commercial industry to do things, but we can't stop there because, as Peter said, our models look different. We can't necessarily depend on those efforts to understand what it looks like in the high consequence space. But we have to make sure that the US has the advantage to use those kinds of systems the way that no other entity on the planet ever has for those high consequences, and we've actually got to be first. So there's some real distinctions between what ML used to look like. We would never have had that conversation that I was just having with you about pattern recognition tools or traditional computer vision. But in these integrated systems where we're putting together experiments and high-performance simulation and thinking about very high-consequence missions, it's a completely different ballgame. And that urgency is something that we all have to sort of grapple with and then move forward on. So see my previous comment about having the will to go forward. It's a clear call to action.
Interesting. So can you think of some non-obvious applications of AI techniques that you're currently developing for, say, energy research? and how you could revolutionize a field that maybe we haven't thought of yet with similar approaches.
Yeah, I mean, I think one of the clearest ones that people may not think about is manufacturing. So when people think of manufacturing, they might be thinking about assembly lines and things that are, early 20th century kinds of production. But modern manufacturing goes through advanced manufacturing, 3D printing with polymers, with printing of metals. These are structural components that can do amazing things, but they come at high speed. AI can revolutionize those kinds of systems. We can understand how to see defects as they're born, recognize that there's a defect, maybe in real time as it's printed, print the anti-defect so that a potentially locally off nominal part has become a globally nominal part. We can add capacity and do entirely new things. It's not that distant from the actual energy conversation that we're having, because if you have a system that can think in real time about data streams, do corrective reasoning, and get better on the fly, you want to do that for a magnetic reactor, for an inertial fusion reactor, for fission reactors, for all kinds of things. So energy and AI can also point directly at manufacturing, and manufacturing for whether it's our stockpile or whether it's for our energy systems can revolutionize the way that we just do production in the US, bringing, again, not just superiority in the AI space, but in general techno-economic competition, where we have the capability to think faster and to build faster than anybody else on the planet.
So kind of like a fantastically fast multi-parameter closed-loop process control. Something like that.
We should come up with an acronym like FAST, but for that.
Interesting. Well, so back to the fuel for all this, the investment. If you had to, this is for Phil, if you had to design an energy investment strategy that would assume the AI progress stagnates, so this is as good as it's going to get, how would it differ from your current approach?
Well, to be clear, we're not doing that, as you can hear from the boss.
Yes.
Look, I mean, I think that things have gotten very, very optimistic in the past few years, and so now, and you're going to hear from Fervo later. This demand side pull from AI is super, super important, and so. If we didn't have this additional demand side pull for what we think are these sustainable energy technologies, I think that would have us go back to sort of say, what are the remaining markets? So that would be a readjustment. Again, I think that's looking good. And then, ultimately, even though we have a lot of upside in our different companies from AI, like very few of the companies, aren't commercially viable without AI. So, I don't think the companies that we invested in so far would have looked very different. But I think that, sadly, it's just a much more pessimistic view of the world if you don't think that there's going to be this new lever arm, both on the demand side and kind of the supply and design side.
Okay. So not to be a Debbie Downer about it, but I do have some questions about, the flip side of this. So for Steve, the question is, what is the most interesting failure you've seen in fusion research, and what did it teach us?
Glad that's your question.
I could trip over that question really bad. I think I think we built experiments in the 70s that we never even turned on, right? And that was a really difficult time because we were discovering the fact that a plasma is so turbulent that the heat gets out so rapidly that it really wasn't worth spending the money to even turn an experiment. So that was a problem. And now, with the advanced computational models and with AI, we won't be making those kind of mistakes again. I want to answer the question that actually somebody else.
Sure. Yeah.
Because I think this is just a cranky old man thing, basically. Which is, I was with a friend of mine, Chris Bishop, who works for Microsoft, and we used to work together many years ago. And we were talking about the simulation of the British weather system that people are doing, and with AI, etc. And he said, we don't have to understand anymore. We don't have to understand. We can predict. So why would we need to understand? And understanding has been the greatest pleasure. So I'm sorry, but I'm not welcoming.
No, I mean, arguably, I think that there is, what it teaches us, I would say, is the value of prediction and AI, so you're not faced with that choice anymore.
I love prediction. I think it's great. But when people say, down there, we're standing,
No, I don't mean that it's instead of.
it's just I'm a cranky on that thing.
That's right. No, fair enough. And so that brings me to another question for Peter this time. What role do you see for collaboration between AI research labs like yours, like DeepMind, and energy companies to advance AI-driven solutions for energy problems?
Yeah, I mean, that's a great question. So, I mean, the first thing I would just say is I think we and a lot of other tech companies have a pretty robust and kind of customizable set of teams that can set up partnerships with different types of or companies and private, public sector groups. And we really, we need that in order to sort of deliver our research into impact. I think, the reality is the AI research labs are really, really good at AI, and they're kind of like amateurs at everything else, right? So like we don't actually know the application areas that well, and we don't really see that as our real mandate. We want to partner. So we see a sort of dependency on experts in fields in order to translate our work into impact. Some examples of this, like again, I was mentioning the weather modeling we're doing. One of the things we've done in our most recent work is we've created this sort of proxy wind power forecasting task, where we take our wind speed and we translate it into wind power by using estimates of power curves. We figure out where the wind farms are all over the world and say, at those locations, this is what our model is predicting the wind power would be. And we show very good results on that against sort of traditional forecasts. But that's not that useful to a wind provider or wind producer, because that's not actually really what they're measuring and what they're trying to forecast. They're trying to forecast actual power coming out of the turbine, and we don't have that data. So that's an example where we need to partner with experts who also have data and know what the exact problem is in order to take the next step. And so we say, if you're a wind provider that wants to partner with us and take the next step with us, reach out. We're seeing this the same thing with our grid optimization stuff. I mentioned before, we're using simulated grids. Again, a grid operator isn't going to find that they're not ready to delete their optimal power flow solvers and replace it with our systems. We need to have real evidence that our algorithms are working in real grids, and we are not able to do that on our own. So I think it's pretty simple, at least speaking for Google DeepMind, and I think probably speaking for most other tech companies. Just email us, reach out, and we'll set up our partnerships team. We'll sit down together with the research partnerships team and figure out if there's a sort of jointly beneficial arrangement for collaboration.
Great. This has been wonderful. I want to leave us with a quick lightning round. I mean, really quick. Starting with Peter. What's the most contrarian view you hold about the future of AI and energy?
So I think it's probably not a very contrarian view for this crowd, but I'm like sort of unabashedly optimistic. I would say that I don't, it's ours to kind of lose this sort of facing this challenge. I think, this isn't to understate the sort of magnitude of what we're talking about, like sort of, revolutionizing the most complex system we've probably ever created, but we're armed with the most powerful tools we've ever created. So I think, I don't think it's a contrarian view, hopefully not at this summit at least, but I would say that for those who think, this is risky, maybe we should, not be going all in on AI. I think that's a mistake. I think that we should go all in.
Steve?
I'm just amazed by the speed at which it was built. This is going to change all of our lives. It's changing our laboratories all over the country as we do it. It's exciting. It's hard to keep up, though.
I would say that, look, AI is amazing. I think we need to be very careful about trusting the results and recommendations from AI too quickly. And so whenever we're looking at applications, we think the sweet spot is AI can help you speed up a parameter space search, but I would still check the math using a traditional method before I build that bridge. And then furthermore, I think we can really optimize AI by not holding it to 100% standard. So for example, if you have a robot that can do 95% of the tasks, whether it's maintaining a fusion machine or whether it's building a skyscraper, perhaps for that last 5%, it can phone a friend, and the friend is a human who takes remote control, does the hard thing, and hands it back over to the AI. So I think, and we worry about this in other domains, it will really slow AI down if there's some catastrophic result because someone was too reckless for it. So I think there should still be a bit of a conservative approach, especially when the stakes are really high.
Great. And Stevie, Brian, this time I'm going to get
I've been called far worse.
So you get the last word.
Yeah, so my contrarian view was going to sound really contrarian until Peter sort of confirmed that it's true. So I'm going to have to twist it. I was going to say that the most successful large companies on the planet actually need the public sphere to go do science, to build out these reasoning systems. And you confirm that, so great. I say that with all of our big private partners as well. Where it is contrarian is with audiences who don't understand the deep technology and they see the enormous successes of the AI world and think that has solved math and physics and chemistry and biology and everything that humans have to think about. That's not the case. So the contrarianism is that we need a partner between the private sphere and the public sphere to make these tools go together. And then what may be contrarian, I guess, a little further is that I'm incredibly optimistic that we can build this out in the United States through the singular advantage, the superpower that we have, which is our public capability that we've spent in science for 10 decades investing in, and the radical transformations in AI, and together, if we do this right, we won't be caught.
Great. Thank you very much. Join me in thanking our speakers. Good.